In this section, we're going to take a look at limits and how they relate to defining continuity.
In an algebra class, you are exposed to the idea of continuity in a very informal way. You are probably told some variant of this statement. If a function is continuous, then that means that you can draw its graph without ever having to lift your pencil. There's probably other ways to phrase that, but it's some variation thereof. So here, this is continuous because I drew its graph without ever lifting the pencil. So this would be continuous. Okay, so if it's not continuous, that means you had to lift your pencil for some reason. There were basically 3 different reasons why you would have to lift your pencil. A function is not continuous if it has a hole, a jump, or a break. One reason I have to lift my pencil is if there's a hole in my graph. I had to lift my pencil to jump over the hole. So this would not be continuous. Okay? So having a hole in my graph makes it not continuous. Having a jump in my graph that also makes it discontinuous. Here, there's a hole. There's no value when when my x value is equal to c, for example. Here, f of c is undefined. Now here, f of c is defined, but it's not here in line with the rest of the graph. Right? So here, that's a hole. Here, there's more of a jump. The point is there, it just jumped away. And the last situation was if there's a straight up break, meaning, oh, you stop, and then your graph continues somewhere else. And these are the 3 basic situations, and of course they can be drawn different ways, but you have 3 ways in which your graph is not continuous. So here's a graph is not continuous. Well, now we're going to be a little more careful about how we talk about continuity, because now we can give a more thorough definition. First of all, when we say a function is continuous, or a function is discontinuous, well, okay, that function is not continuous, right? Right. What if I cover this part? Would that be continuous? I can draw this without lifting my pencil. Okay, so that looks like it's continuous. Wait, but we just said the graph's not continuous. So how does that work? I mean, it's not continuous, except it is, kind of. Over here, same thing. If I look at just this part, I can draw the graph without lifting my pencil. And same thing with this side. I can draw the graph without lifting my pencil. So this is continuous, and so is this. But this is not continuous? Is that how that works? Well, so when we talk about continuity, we don't really have a continuous or discontinuous function. What we have is there are places where your function is not continuous. So here we don't say this is a continuous function or it's not continuous. What we say is it has a discontinuity, or we can say it's discontinuous at this value. So here, all 3 of these, and there's 2 ways to say them. You can either say they have a discontinuity, at x equals to c, or you can also just say the function is discontinuous at x equals c. And either of those means the same thing. Okay, so this is the kind of thing you would have seen in college algebra. It's continuous because I can draw the whole thing without lifting my pencil, and it's not continuous if I have to lift my pencil. Here we're being slightly more exact by what by the way we say it's not continuous. Really what we mean is it's not continuous there. It's continuous other places. Notice right here, this can be drawn without lifting my pencil. Oh, but it's not continuous there, or there, or there. Okay, but now let's be a little more formal about this. The reason that you were given this working definition in algebra and continue to use it in trigonometry and up until now is because the formal definition of continuity relies on knowing what a limit is. And although we have not formally defined a limit here, we have defined enough to be able to make sense of the following definition. So this is the actual definition of continuity. Let's begin with a function. Let f be a function and a be a real number. Then we say f is continuous at a point, continuous at the value a, continuous at a, if all three of the following things are true. First of all, you have to be able to plug in a into your function. So here f of a is defined. So it doesn't matter if you plug in a and you get 5 or a million or negative 12, it doesn't matter. As long as you get something, you should get 0 over 0 or 5 over 0 or whatever. It should be defined. That's why right here, this is discontinuous at c, because I can't find f of c. So note right here, f of c is undefined. And because it fails that first condition, that means it's not continuous at c. Okay, but that's not the only thing required. For example, here, this is also discontinuous at c, but I have f of c, it's right there, look. There's f of c. And right here, f of c is defined, it's right there. There's my y value, so if x is equal to c, then f of c is going to be this y value right here. So in both of these cases, f of c is defined. So obviously that's not enough. It's not enough to just have the definition. Well, the next thing is that not only does the f of a have to exist, but we have to be able to define the limit as x approaches a. So the limit as x approaches a of f of x is defined. It exists. That's the problem with this one. Here, f of c is defined, it's right there, but the limit is not defined. From the left, it's going to be one thing, and from the right, it would be a different thing. Right here it would be 2.5, and over here it would be 3.5. So even though the f of c is defined, the limit as you approach c of f of x, that is not defined. So that's why having a jump in your graph tells you that it's undefined there, because you're missing that second condition. Okay, so that's why these two are undefined, but what about the middle one? After all, f of x is undefined. Look, it's right there. And the limit's defined, because look, I come from the left and I come from the right. I have a limit, it's right there. But notice how they're in different places? F of c and the limit are not in the same place. That's the third condition. Not only does f of a have to be defined, not only does the limit as you approach a of f be defined, but also they must be equal. The limit as x approaches a of f of x must be the same as that f of a. And that's the problem with this middle one. Yes, the limit exists. It's right there, that little bubble right there. And yes, f of a exists. It's that point right there, but they're not equal to each other. So here we have the reason this one is discontinuous at c is because the limit as x approaches a of f, limit as x approaches c of f of x is not equal to f of c. And because of that, that's discontinuous. All right, so let's take a look at some examples of this. Let's talk about a function, and let's consider whether or not it's continuous at a particular point. All right, so the question is the function f of x equal x plus 7 over x minus 7, is this continuous? And it's going to be a two-part question. At the number 7 and at the number negative 7. All right, so two-part question. All right, well, if it's going to be continuous, and here we're going to do these one at a time. So let's start with checking to see what's continuous at 7. Then what that means is, first of all, I should be able to plug in the number 7. Okay, so let's see what happens. First thing I need to do is find f of 7. If there's any of these I cannot do, then no, it's not continuous. But if I can do all three, then yes, it's continuous. All right, so let's try that one with number 7. If we try f of 7, that's going to be 7 plus 7 is 14, over 7 minus 7, which is 0, and right away we're done. This is undefined, which means it fails one of the conditions for continuity. So f of x is not continuous at 7. It doesn't matter if we were able to do the other two. If even one of them fails, that's it, you're done. F is not continuous at c equal to 7. Or I guess let me use the same letter they use here, at a equals to 7. All right. Let's try the other one. Let's see if it's continuous at negative 7. Okay, well again, you have to, first of all, you have to be able to plug in the number. All right, well that's f of negative 7. All right, well that's going to be negative 7 plus 7, which is 0. And then negative 7 minus another 7 is negative 14. That's fine. That's just equal to 0. All right? Undefined is if the denominator is 0. If just the numerator is 0, that's fine. Okay, so great. So that is defined. But that's not enough. We need to be able to make sure that the other two are satisfied as well. So the next thing we want to do is we want to say, okay, that checks out. But now let's find the limit not plugging in negative 7, but the limit as x approaches negative 7 of x plus 7 over x minus 7. All right, well, let's see what happens there. First of all, let's try to plug it in. Now, remember, if it gives you 0 over 0, that's undefined. There's nothing we can do about that. We'd have to find some other way to evaluate. We could build a table, right? Try to plug in numbers that are close to negative 7. Or we could try to simplify this using some kind of algebra. We can rationalize a numerator or a denominator or factor. But first, let's try the simple thing, because it might work. We take the limit as x approaches negative 7 of x plus 7 over the limit as x approaches negative 7 of x minus 7. Remember, when you take the limit of a fraction, you can do the limit of the top separately from the limit of the bottom. But now, since this is the limit of a polynomial, I can plug in that number and hope for the best. Negative 7 plus 7, that's 0. Negative 7 minus 7, that's negative 14, which again is 0. Okay, good. So I was able to plug in my number, and I was able to find the limit of my number. Okay, so I was able to satisfy the first two conditions. But now the third condition, and once you have the first two, the last one's pretty easy. You just have to make sure they're equal to each other. Yeah, right here, look, they're both equal to 0. Here, f of negative 7 is equal to 0, which is the same as the limit as x approaches negative 7 of f of x. So because plugging in negative 7 is the same as taking the limit as you go to negative 7, that satisfies the third condition. And so your function is not continuous at a equals 7, but your function is continuous at a equal to negative 7. Just like that. All right. Let's see another example of this. And let's make our function just a little more involved. Here we have a piecewise defined function. Let's say f of x is equal to, and this is going to be defined in 3 pieces, x plus 6, and this will be true whenever x is less than or equal to 0. It will be a constant value of 6 whenever x is between 0 and 2, not including 0, but including the number 2. And then x squared plus 1 for whenever x is greater than 2. So now the question is this defined at, is this continuous where the jumps are? Is this continuous at 0 and is this continuous at 2? Is f of x continuous at a equals to 0 and at a equals to 2. All right. Now, first of all, you might wonder, well, why am I not asking about anywhere else? Why am I not asking about, is it continuous at 4 or 12 or -9? These are all polynomial. That's a constant, which is technically a polynomial. One thing that you can kind of take for granted, and we'll talk a little more about it in the calculus course, a little more formally, but one thing that you can pretty much always take for granted is that polynomials are always continuous for every number. So here, we're just gonna take this for granted for now. But note, a polynomial is going to be continuous for all real numbers. We already know that a polynomial is defined for all real numbers, but it turns out that it has a limit for all real numbers as well, and that those limits are always the same as what happens when you just plug in the number. Okay? We've seen a little of that previously when we talked about properties of limits, and here we're going to, without being any more formal than we have already been, we're going to go and take this for granted. A polynomial is continuous for all real numbers. In a formal calculus class and a Cal 1 class, we will investigate this a little further. But this statement for now is sufficient to let us know that, hey, look, that's a polynomial. So it's going to behave this way whenever x is less than 0. So as long as x is less than 0, we're fine. Here, it's going to behave this way between 0 and 2. So that's fine. It's always going to be continuous between 0 and 2. And this is going to be a polynomial whenever x is greater than 2, which again, since it's a polynomial, it's continuous for all numbers greater than 2. The only place where you might have issues is where there's a jump from one to another, because that's where your graph can have holes, jumps, or breaks. Everywhere else, we know it's a polynomial. Essentially, your graph might look like this. It might look like this, and then it'll jump to another polynomial somewhere else. Right? Or it'll look like this, and it'll jump to somewhere else, and then jump back, because after all, this is defined in 3 pieces. So the only places where it might be discontinuous, maybe it is, maybe it's not, is going to be at the transition points, at 0 and at 2. So that's why those are the only ones we need to bother worrying about. Right? So let's go and try those one at a time. Let's go ahead and, first of all, let's see what happens when a is equal to 0. Okay, so first of all, f of 0. You have to be able to define it first. All right, well, f of 0, oh, sure, right here. When x is less than or equal to 0, I plug it into this one. Okay, so plug in 0 into this one. 0 plus 6, which is 6. All right, no problem there. Now, the next thing I need to do is I need to be able to take the limit. I need to take the limit as x approaches 0 of f of x. Okay, well, the limit as x approaches 0. If I come in from the left or if I come in from the right, oh, well, let's see. There's 2 different functions on either side, so maybe I should check them separately. Let's see what happens to the limit from the left. If I'm coming into 0 from the left, that's from this side, where numbers are less than 0. Okay, if I take the limit as x approaches 0 from the left, I'm plugging in numbers like -1, -0.5, -0.1. I'm going to approach 6, because here these numbers are getting closer and closer to 0. which means a number that's very close to 0 plus 6 could be just 6. Or, more simply, if you realize that this is a polynomial, whenever you take the limit of a polynomial, what you're doing is you're plugging in the number into the polynomial. That doesn't work for other functions, but for polynomials it does. So here, if you plug in 0 plus 6, that'll give you 6. Oh, but that's only the limit from the left. What about from the right? Notice here, from the right, it's a totally different function. Okay, so that's going to be the limit as x approaches 0 from the right of my function. Well, notice that from the right, it's a constant. And one thing that we've learned is that when you take the limit of a constant, it just stays that constant. That's the thing about constants. They don't change. So it looks like the limit from the left and the limit from the right are equal to each other. Oh, okay, cool. So if the limit from the left and the limit from the right are equal to each other, that suggests that the limit overall, the limit as x approaches 0, not from the left or from the right, but just approaches 0, is equal to that 6. So here we've satisfied our first condition because we were able to plug in the number. Here we've satisfied our second condition because we were able to find the limit. And now our third condition, we need to make sure those are equal to each other. And they are. They're both equal to 6. Here f of 0 is equal to 6, which is equal to the limit as x approaches 0 of f of x. So that concludes my third part of my conditions, and so because my function satisfies all three conditions at a equals to 0, that means yes, my function is continuous at 0. All right, awesome. Let's check 2. Okay, first of all, we're going to try to plug in 2. We have to be able to plug it in first. Okay, well, right here, the limit as x approaches, oh, not even limit, right now I'm just plugging in. So when x is equal to 2, I'm plugging it into this portion. Oh, well, that's a constant. So that's always going to equal to 6. So if x is equal to 1 or 1.5 or 1.9 or 2, it's always just equal to 6. All right, so that checks out the first condition. The function is defined there. Okay, now let me go and find my limit. I need to find the limit as x approaches 2. And again, it's going to be different from either side, so I need to check both sides. I have a different function on either side. So if I'm approaching x is equal to 2 from the left on my function, that's doing it from this side, from 1 and 1.5, numbers that are slightly less than 2. And I notice that on that side, I have a constant. Okay, well, if I take the limit of a constant, that's just a constant. So that one's not hard at all. It's just the limit of a constant, which is just going to stay that constant. Now let me try from the other side. Let me take the limit as x approaches 2 from the right. Okay, well, that's going to be from this side. Oh, the nice thing about taking a limit from the right is that it's a polynomial, which means I can just plug in my number. All right, if I'm taking the limit of something else, well, then no, I can't just plug in my number. For a polynomial, I can. Okay, so take the limit as x approaches 2 from the right. That means I'm using this polynomial because that's to the right of 2. And if I plug in 2, that's 2 squared is 4 plus 1 is 5. Oh, those are not equal to each other. And because the limit from the left is not the same as the limit from the right, that means overall the limit as x approaches 2 of my function does not exist. It's not defined. And because it does not exist, this fails the second condition. The limit is not defined. It does not exist. So that means that my function is continuous at 0, but not at 2. The function f of x, as defined up here, is continuous at a equal to 0, but not at a equals to 2. Just like that. Incidentally, there's a little bit of language here. Earlier I said a polynomial is continuous for all real numbers. That's one way to say it. You can say a polynomial is continuous for all real numbers. When a function is continuous for every number, you can say it that way, for all real numbers. You can also say a polynomial is continuous everywhere. And everywhere is just another way of saying it's continuous for every number. Right? So those are interchangeable. All right, so go ahead and give this a try. Take the following function and find all values for which it's not continuous. Now you might say, well, I have to check every number in the universe? No, because let's see how this function is defined. Here we're going to define this function as f of x. Oh, I guess I should write the question, right? Find all values for which this function is undefined. And the function is given piecewise. F of x is equal to, and it's given in 3 parts, x plus 7 whenever x is less than or equal to 0. It's equal to 7 whenever x is between 0 and 3, not including 0, but including the number 3. And it's equal to x squared minus 1 whenever x is greater than 3. So go ahead and give that a try. Now again, we're looking for all values for which the function is undefined. You might think I have to check every number, but notice that in between here, all of our components are polynomials. So think about that. Go ahead and pause the video, give that a try, and once you have found all values for which the function is undefined, go ahead and unpause the video and we can go through that together. All right, so let's take a look. Here, this is polynomial whenever x is less than 0. So we know it's continuous because polynomials are continuous for all real numbers. Here, that's a constant, which is technically a polynomial. So between 0 and 3, it is continuous. And when x is greater than 3, that's a polynomial, so that's continuous. The only places where it might be discontinuous is in the transition points, at 0 and at 3. The places where you switch from one graph to another, the places where you switch from one type of polynomial to another. So the only places we need to check are 0 and 3. So we're going to need to check a equals to 0, and we're going to need to check a equals to 3. Let's start with 0. All right, so to check if it's continuous at 0, first we have to try to plug in 0 and see what happens. All right, well, if we plug in 0, here, you're going to plug it into this first rule because x is less than or equal to 0. That's where this belongs. So 0 plus 7 will be 7. Okay, so we are able to plug in 0. Okay, well, it's not enough to just be able to plug it in. We next need to be able to find the limit as x approaches 0. And since you approach 0 using different functions on either side, we're going to have to take the two-sided limits and compare them. All right, we don't just have a single function that we can use. We have to use a different function depending on what side we're on. Okay, so we're going to have to check both of those. From the left and from the right. Okay, well, from the left, we're using this, where x is less than 0. Okay, well, coming in from the left, that's a limit of a polynomial. And the nice thing about the limit of a polynomial is you can just plug the number right in. Okay, so plug in the number. I'm trying to approach 0, so let me just plug in 0. 0 plus 7 will give me 7 as my limit from the left. Okay, now what about from the right? Well, from the right, I'm using this region, where numbers are bigger than 0. Okay, well, it doesn't matter what I plug in. This is the limit of a constant. Oh, and limits of constants are just going to stay constant. It's going to stay 7. And so that means the limit from the left is equal to the limit from the right. So that means that the limit as x approaches 0, not from the left or from the right, but just overall, is equal to 7. So far we've satisfied our first condition by being able to plug in 0. We've satisfied our second condition by being able to find the limit as x approaches 0. And finally, our third condition is can we have these equal to each other? And, well, once you find both of these, the third one is pretty much automatic. Yes, they're equal to each other. Here you find that f of 0 is equal to the limit as x approaches 0 of f of x, which satisfies our third condition. They're both equal to 7. So here your function is continuous at 0. Okay. What about 3? Let's see. Let's try to plug in 3. F of 3, that's going to plug into this one right here, because that's what happens when x is between 0 and 3, including 3. Oh, and that's a constant function, so it doesn't matter what you're plugging in. As long as it's in this region, you're going to get the number 7. Okay, so f of 3 is 7. Okay, next let's try to find our limit. Take the limit from the left and from the right, and we do have to use different ones. We do have to compare each one, because from the left we're using one rule for our function, and from the right we're using a different rule when x is greater than 3. All right, so the limit from the left, well, from the left you're using numbers that are less than 3. Oh, that's this region here, which means you're taking the limit of this constant. Oh, and that's the nice thing about limits of constants, they stay constant. All right, now let's take the limit from the right. The limit as x approaches 0 from the right of, sorry, that should be approaches 3, not 0. Because here we're checking 3. So now, taking the limit as x approaches 3 from the right, well, that's going to use this one, where x is greater than 3. Right? From the right of 3, greater than 3. Okay, well, that's the limit of this polynomial. And the nice thing about the limit of a polynomial is you can plug in the number. All right, so that's going to be 3 squared, which is 9, minus 1, which is 8. Oh, but that means the left limit and the right limit are not equal to each other. Oh, so that means that the limit as x approaches 3, not from the left or from the right, but just the limit, does not exist. And that's it. Since we have failed to meet one of the conditions of continuity, that means that no, our function is not continuous at 3. So we know it's continuous for every number except maybe 0 and 3. Oh, but we found that it was continuous for 0. Oh, but we found it was not continuous for 3. Okay, so that means 3 is the only number in the universe for which this function is not continuous. And so f of x is, and there's a few ways to say this. You can either say it is discontinuous, only at a equal to 3. That's one way to say it. Say, okay, this is the only place where it's discontinuous. Or you can say the opposite. You can say it's continuous everywhere except at a equals 3. So either discontinuous at one point or continuous everywhere except one point. And both of those are perfectly acceptable ways to say that. F of x is continuous for all values except a equals to 3. Here we know it's continuous for, so you have your number line. That's a polynomial when x is less than 0. Okay, so we know it's continuous less than 0. It's a polynomial, a constant, between 0 and 3. So we know it's continuous between 0 and 3. And it's a polynomial greater than 3. So we know it's continuous for all numbers greater than 3. So the only places it might have been discontinuous were at 0 and at 3. Oh, but we found it was continuous at 0. Okay, so fill that in. Oh, but it was not continuous at 3. So it's continuous for every real number except at 3. Continuous for all values except at a equals 3. Or you can say it's discontinuous only at 3. And both of those mean the same thing. That brings us to the end of our section. Note this is not an exhaustive experience with the concept of continuity. There's a few things that have been glossed over and not really investigated. In particular here, we're only talking about polynomial functions or piecewise polynomial functions. We don't talk at all about trigonometric functions or really any other kind of function. Also, there are some connections between continuity and some other concepts which we won't mention here, which are part of a full calculus course. However, here the thing to take away is that we do have finally a formal definition of continuity. And although we have not fully defined the limit, we have defined it enough that this full formal definition finally is accessible to us. So that is it for the section. That is it for this topic, at least until Cal 1. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.